Okay, so good afternoon, and welcome to the first seminar in the 2024 series of the Material Digital Humanities seminar series. The speaker in today's seminar is Professor John Aycock from the University of Calgary. He's a professor of computer science, and I won't give the detailed bio and introduction because John is partly going to introduce himself and also explain a bit about how he got into this topic and some of his publications in this area as part of the introduction to his paper. But John is going to talk to us about Archaeogaming Antics, computer science meets archaeology. Please, John.
Well, thank you all for coming. Thank you for the opportunity to speak with you today. I don't want it to get lost at the end, so let me begin by saying that much of the research I'll be talking about today has been done in collaboration with a variety of colleagues and students. And in particular, I'd like to mention my longstanding anthropology and archaeology collaborator, Dr. Katie Bittner at MacEwan University in Edmonton. So I want to begin with a question, I suppose a rhetorical question since we're on Zoom. How many of you play video games? Any video games, match 3 games, first-person shooters, MMO, Minesweeper. Here's the thing, I suck at playing games. And I appreciate the irony because what I do in my research now is study games and their implementation, specifically old retro games. Now, you might think that compared to the games you play, these games look like garbage. But you need to remember the historical context. Most of the game genres you enjoy now arose in this early time period of the 1970s and the 1980s as the game industry formed and developed. The programmers made these not knowing what constituted a good game or for that matter, what a game controller should look like. They invented this. And the computers and the consoles they programmed for were wildly constrained in terms of memory and compute power and storage. So even the most terrible looking game may be a minor technical miracle in terms of its implementation. And they used techniques that aren't commonly taught anymore in computer science, yet they are techniques that still have modern applications. I wrote about a bunch of this in the book, this book from 2016 specifically, and I'm happy that I did that. I am less happy with the book's name in retrospect because I'm not a trained archaeologist, and that's something that becomes important shortly. But for now, what is retro game archaeology? I defined it in terms of what I call the 3 T's, the tools, the techniques, the technology used in old games implementation, and contextualizing these in a bigger picture view. Not just saying, E.T. did this one thing and stopping, but finding these other 2 games that did the same thing and putting it into the more general context of, in this case, memory management techniques, and then a broader context in time to connect the idea to modern applications. But it was not about playing games, and it wasn't a quest to find things in the first games or the most prominent games, because certain implementation techniques can be very rare. So I'd written this book. Once the book was done, where do I go from there? What do I do next? Well, never doubt the value of professional networking. By chance, I was talking with a colleague of mine here at the University of Calgary, Dr. Lisa Hughes. I was talking with her about this research I've been doing, and she asked me one critical question that changed the trajectory of my research. Have you heard of Andrew Reinhardt? Andrew Reinhardt is an archaeologist, a real archaeologist, unlike me. You may have heard that there was an urban legend about old Atari video game cartridges that got buried in a landfill in New Mexico. And in fact, there was a documentary in 2014 called Atari Game Over that literally uncovered the truth. And Andrew, seen here on the right, was one of the archaeologists on the dig site for that. At the time I first became aware of him, he was a PhD student at the University of York in the UK, and he was busy building a new area of research within archaeology itself called archaeogaming. When I chose the title Retro Game Archaeology for my book, I had Googled a whole bunch of related terms to see what existed, and never in a million years would I have thought to try archaeogaming. I had completely overlooked it. Eventually, in 2018, Andrew would go on to write the first book about it, but that was still in the future when I initially contacted him. So Andrew defined archaeogaming broadly as the archaeology both in and of digital games. Now, I knew of some other areas of study that looked at games or software or history, and here I've arranged them based on the amount of technical detail that tends to be found in them. But archaeogaming? What is it? Where did it fit in? Well, archaeogaming is extremely inclusive, and this chart shows some of it. This chart is hard to read because archaeogaming includes so much. For example, archaeogaming includes physical excavation of digital video game artifacts, like at the New Mexico site. It includes the portrayal of archaeology and archaeologists in games. It includes conducting real archaeology in virtual game worlds. It includes what I was doing, studying the implementation of old games. In other words, it wasn't a matter of how retro game archaeology and archaeogaming differed. Archaeogaming had room to include retro game archaeology. I was already an archaeogamer and I didn't know it, although there wasn't research like I did within archaeogaming yet. But what is archaeology? I had never taken an archaeology course in my life, never interacted with archaeology colleagues on our large campus where the archaeologists are located somewhere in that direction. My only real impression of archaeology was what I had learned from popular media, and spoiler alert, Hollywood representations of archaeologists, not always accurate. So naturally, I turned to the source of all that is true, Wikipedia. One thing archaeologists study is artifacts, things that humans have created and used and discarded, things that humans affected and in turn were affected by. Are there artifacts related to video games? Of course. There are physical artifacts, although less so for games in the year 2024 than there were in, say, 1980. What I was really interested in was the game implementation, though, not the physical artifacts, but the digital artifacts, the code and the data stored within the physical artifacts. And that's where things get a little confusing. There's very little work in archaeology studying digital artifacts, despite how many digital artifacts there are. Age isn't the issue either, because there's an entire field of contemporary archaeology that studies more modern things. Maybe archaeology isn't a good fit. Maybe this is really a job for history. Now, one way that history and archaeology have been differentiated in oversimplified form is that archaeology deals with artifacts and history uses written text. So if history deals with text, the next question is a game text? And the answer is definitively maybe. If you're a computer scientist, when I say text, you might first think of a plain text file as text. Or if you had an all text game, a text adventure like Zork, then we could agree that this game is a text. In the humanities, as you may know, a text is interpreted very broadly. If you were to view this from the perspective of the field of game studies, for example, which is much more closely affiliated with the humanities, then yes, a video game is a text. There's a practical reason for it, because by thinking of a game as a text, then techniques from, say, literary theory can be applied to it, like Girard Genet's notion of paratext as a framing device. Closer to the work I'm talking about, reverse engineering games, a game is a text on completely different levels. The bytes of the game contain the machine language of the game that brings the game to life. And even though this language is read by the computer, it's still a language. It is a text. And we can disassemble that machine language, automatically translating it to create a more human readable version that is increasingly recognizable as a text. And as a text, it's fair game for history, right? Again, yes and no. The work that I do would fall under the category of technical history. And as the historian Thomas Haig pointed out, the technical history of computer science is greatly understudied. It makes sense from a cultural perspective. Computer science is always busy glorifying new things at the expense of studying the old. But if history has moved away from technical history, where does that leave me? Yes. Before I knew it, I was collaborating with archaeologists studying video games. So let's revisit this. I am still not an archaeologist, but the things that archaeology as a field does not do, studying digital artifacts and applying archaeology to computers, these are things that I can do. But I cannot do it alone because, as I may have mentioned, I'm not an archaeologist. This has really become interdisciplinary research. I now work with archaeologists to study the implementation of old games. And for me, the computer science archaeology collaboration makes sense. Archaeologists have been studying humans and how they create and interact with technology for longer than computer science has existed. Why would you not include archaeologists? And programming, it's a human endeavor, and humans change much less quickly than our technology does. Yet meanwhile, the part that falls outside the archaeological area of expertise, understanding digital artifacts, that is what computer science can contribute. But working with digital artifacts does provide some challenges as well as opportunities for traditional archaeology. Now, I'm going to move off the slide before the font kerning police show up. Just change the share here. Here, I have a computer game that you could easily argue is a single artifact. I can obviously hold it in my hand, and we can physically measure and examine it along with the contents that happen to be contained inside it. So this particular folder has some paper manuals inside it, as well as some discs here. But now if we take this magnetic floppy disk, which contains the actual code and data that the computer runs to make the game, and look at it with special equipment, With this special equipment, we can actually see the patterns of magnetic fluctuation on this disk made visible. In fact, with a trained eye, you can see the logical disk structure and hints about the game's copy protection in this visualization. So this gives us a connection between the physical and the digital worlds. And what I study is the digital artifact that's magnetically encoded on this disk. There are so many facets and layers to the digital artifact, this game specifically, but others too, that you can equally consider this disk's digital contents to be a site as much as an artifact. But unlike a physical excavation site where there would be much hand-wringing over where to excavate and how much to excavate, and that we would only get one shot at the site because physical excavation is destructive, what I do, excavating a digital artifact, is repeatable. It's science. Someone else can come along and independently validate, or for that matter, refute my result. Moreover, we are not limited by other physical constraints, like having to excavate a higher layer of dirt before reaching the lower layers of dirt. There's much more flexibility with digital artifacts. If you're interested in this particular game artifact site example that I have in my hand, I published a book in 2023 that does an extremely deep dive into it, along with how to go about the sort of reverse engineering work that I do on digital artifacts, where I start with the binary ones and zeros the computer sees and gradually reconstruct meaning from them, like solving a complicated puzzle. I don't want to go quite that far in depth today, though, so instead let's start with an overview. What are we finding out from our work? Well, we're learning about human ingenuity and programmers' development practices and trends over time, yada, yada, yada. This last point is easy to gloss over, though. Computer science as a discipline is still relatively young, and we are reaching an inflection point where we need to contend with hardware and software where we may only have a fragmentary record, where the people who made it are no longer with us. The precise things that archaeologists are used to dealing with. So through our work in archaeogaming, we are actually laying the foundation of how to study software 10, 20, 30 years from now. Should you be seeing some slides now? Yes, you should. Gabby, are you seeing slides?
No, sorry, we're still seeing your desk, your document scan.
Thank you, Zoom. Okay, let's try this again.
I'm glad Keith pointed that out.
Yes. Okay, are you seeing slides now?
Yes, we're back to your slides here.
Okay, and are they changing?
Yes.
Okay, great. Thank you for flagging that. In that case, let me skip back for a second and show you this pretty picture once again, because this is an awesome visualization. Okay, so now that we're back with slides, let's look at a few examples to make this more concrete. And this is work with Katie Bittner. In this example, I worked with Katie on the 1980 game Mystery House on the Apple II computer. The game was the first one designed by noted game designer Roberta Williams, and it was implemented by her husband, Ken Williams. This was the first game published by their company, a company that would eventually be renamed CR Online. You might think that Mystery House looks crude, and it does. But the historical context is that this was the first graphical adventure game, the first time a text adventure game had been augmented, been illustrated with graphics. It would have been an amazing contrast to any other adventure game of the time. And we wanted to look at its implementation, but its source code, as far as we know, was lost decades ago. This is a job for reverse engineering. The most prominent feature of Mystery House is the graphics, of course, whose format we reverse engineered and discovered that there's two different methods used. We know from historical sources that Ken and Roberta Williams used a new device called a VersaWriter to manually trace and digitize Roberta's drawings for the game. From our reverse engineering of the data format, we can reconstruct the drawings directly from the game's data. And moreover, we can see how they were traced in the VersaWriter. So effectively, we're able to follow their hand as they traced Roberta's drawing 40 years later. The other graphics method was used for finer grain detail than would probably have been possible with the VersaWriter. We can reconstruct those directly from the game data as well. Through reverse engineering, we could additionally extract the game logic which Mystery House interpreted. Although I should point out, in this case, we don't know what the original language looked like, if indeed there was one. So this representation is for convenience only. Obviously, there is more to the game logic than I can fit on this slide, and this is only a fragment. But on the topic of fragments, sometimes with old games, you get lucky, and fragments of the game's source code happen to be lingering in the computer's memory at just the right time and accidentally got saved with the game. I've seen this for old video game cartridges before, and so it was something I checked for on the Mystery House disk. There did seem to be some code captured, but it was garbled and not completely readable. I realized that this was a compact encoding used by the assembler, the tool that Ken Williams used to write the game. And I reverse engineered that assembler format so the Mystery House code fragments could be extracted. What you are now seeing is part of the lost source code for Mystery House. These fragments told us a lot. For example, we know exactly which assembler Ken Williams used, and combined with reverse engineering, we know what tools he chose not to use as well. Now, Ken Williams was popularly lauded as a programmer, and we could evaluate these claims firsthand, noting that he used some good programming practices, and interspersed with that, we also see indications that he was not yet an expert in assembly code for this particular computer. We also know from code fragments that the person who translated the game into French, Tom Nelevanko, had access to the game's source code. One surprise from the reverse engineering was that the graphics code, so prominent in Mystery House, was not written by Ken Williams at all. It was using code from Apple that was written by Apple co-founder Steve Wozniak in 1977, and we could positively identify the original source. There are other things that we found, but what made me particularly happy about this work is that my archaeology collaborator, Katie, was able to frame what we were seeing in terms of the archaeological notion of the chaîne opératoire, or operational chain, which allows us to think of what Ken and Roberta Williams did with Mystery House in a more general human technological framework. What they did is a continuation of what humans have done since time immemorial. This next example is work with Tara Copplestone looking at a game for the Atari 2600 console. The Atari 2600 you see here was an early influential game console with a surprisingly long lifespan, and it was very constrained. For its memory, it only had 128 bytes of RAM. Or to put it another way, this picture you're seeing of the Atari 2600 is 3 orders of magnitude larger than the amount of memory the console itself had. In particular, we looked at the 1982 game Entombed. I had picked this game somewhat arbitrarily for my retro game implementation course as an assignment, but it turned out to be surprisingly interesting. The premise of the game is that, excuse me, premise of the game is that you're an archaeologist and you have to run through a maze and avoid zombies. I'm told this happens all the time in archaeology fieldwork, except the archaeologist and the zombie don't look like these drawings. On the Atari 2600, they look more like this. Entombed was a maze-based game, and mazes were featured in a number of early games. This particular maze in Entombed continually scrolled upwards, and you can see that the maze layout was symmetric. You can also see that this maze by itself is unsolvable. You can't make it through to the bottom. But the game has these rectangular make-break devices, this rectangle you see floating in the upper right. And you can use that to punch through a maze wall if necessary. We had a number of results related to this game, but I want to focus on only one right now, and that is how the maze was generated. Reverse engineering the game, we discovered what seems to be a unique way of generating mazes. Because this maze is scrolling, a row at a time needs to be generated. And memory constraints on the Atari 2600 meant it would be impossible to generate an entire maze ahead of time. It all had to be done on the fly and quickly as the game was being played. But in fact, due to the symmetry of the maze and the fixed wall on the left-hand side, only one portion of a new maze row needs to be computed, and the rest comes for free by taking advantage of the Atari 2600's hardware. And of these 16 bits that need to be generated, each one is duplicated. So the maze algorithm very cleverly needs to only select 8 bits for a new maze row. Now, obviously, the 8 bits can't just be all random. You want to have previous walls and passages continuing from place to place in a well-designed manner. Entombed's algorithm selects a new bit for a maze row using a Tetris piece-shaped amount of context, 5 bits of it. Here, the context bits are shown in white, and the bit to be generated is the yellow X. Now, initially, some of these context bits are located in the omnipresent wall on the left-hand side, and they're initialized with 1 and 0 and a random bit to give some variety. Then after the first bit is selected, the Tetris piece context slides to the right, and the next bit is selected, and the next, and we continue on until we get to the last bit that needs to be generated. This context is now drawing on redundant information across the line of symmetry, and the final context bit is randomly chosen instead. Now, how are the 5 bits of context used to decide at each step whether a wall is present or not? 5 bits are used to index into a mysterious 32-byte table in the Entombed code, and that tells the algorithm whether the resulting bit is a wall or a passage or one of the two selected randomly. At the time, we performed some analyses and concluded that the table's values were probably manually chosen. Problem solved. This does act as a segue into some follow-on work, though. You may recall, a mere 2 slides ago, that we had found what I call the mystery table. Well, funny story. It turns out that mysteries make for compelling narratives, and Chris Braniak wrote a piece about our work for the BBC Future site. And thanks to this BBC article, this problem inadvertently got crowdsourced, and my mailbox got flooded with theories from people as to how this mystery table worked. I found out later that someone had added it to Wikipedia's list of unsolved problems in computer science page. Well, let me back up. I learned that Wikipedia had a list of unsolved problems in computer science page, and that someone had added Entombed to that list. There was actually a relatively recent paper published, not by us, claiming to have solved it. So again, problem solved. Not so fast. The New Yorker Radio Hour podcast did a follow-up story about a year and a half later, and they did some really good investigative journalism and managed to find someone who was central to the entombed maze story, but whom we hadn't been able to track down before. Paul Allen Newell, seen pictured here as he looked in 1982. After the podcast came out, the folks from the New Yorker Radio Hour put us in touch with each other. When you think about the seven wonders of the modern world, you might think of the Great Wall of China or Machu Picchu. But I want to make a case for one of the seven wonders of the modern world being Paul's garage. Because in his garage, Paul has retained artifacts related to his professional life dating back decades. Printouts, manuals, old floppy disks with source code. Usually when we study an old computer game, we have one artifact to work with, the game. Overnight, with Paul's treasure trove, we ended up with nearly 500 artifacts related to the development of the maze in Entombed, complete with a finished yet unreleased game based on the same maze code. So, what was the mystery table? Suddenly, we had the original documentation Paul wrote to describe the maze algorithm devised by Paul and his friend, the late Duncan Muirhead. You'll notice the Tetris-like conception, like we had in our original paper. And with all these artifacts, we drew on methods from traditional archaeology to manage them. And here you can see a Harris matrix that Katie made so we could track the lineage, the layers of the different versions of the code we found, building on an idea by Andrew Reinhard. One thing I think is really neat about this work is that Paul wasn't just a passive agent in all this. He didn't just supply us with the artifacts and some oral history and exit the picture. He actively worked with us to study the code artifacts and was also heavily involved in writing the paper. In other words, we weren't just imposing our own interpretation on these artifacts and past events. Of course, from an academic viewpoint, that raises questions about things like objectivity, and that was something we needed to navigate as we did this work. In these examples so far, I've been talking about the study of single games. Although, as you saw in the last example, we might, if we're lucky, end up with a large number of artifacts related to one game. But obviously, there's a lot of games. You might wonder if what we do scales up to large corpuses of games. And the good news is that, yes, it does, given the appropriate tools. The bad news is that's basically a whole other talk. But just to give you a flavor of what that looks like, I want to tell you about one last example that actually began with Entombed. In addition to Entombed's maze, the game had what's called a pseudo-random number generator, code that would produce random-ish numbers for gameplay. I simplified it here to make it more readable. The code's basically producing random numbers by manipulating two values that I've labeled WX and YZ. So it's performing a calculation. As a computer scientist, it's reasonable to ask what algorithm the game is using to produce random numbers. In other words, what type of pseudo-random number generator does Entombed have? Well, it is almost what's called a linear congruential generator. Almost, except for the presence of a very subtle bug in the assembly code. This bug now acts as a signature that we can use to find the same code in other games and gather empirical evidence of code reuse practices. Let me put this another way. You may not understand this assembly code, but you would probably agree that the code on the left from Entombed is identical to the code on the right from the game Towering Inferno. Code would seem to have gone into Entombed or come out of Entombed, especially when you consider the presence of the distinctive bug. In fact, at the time, we could trace that code to 5 other games, so we could demonstrate how code could migrate from game to game, even in the absence of us having source code or relying on firsthand recollections from game programmers. After I'd given a conference presentation at an archaeology conference about this early Entombed work, I was talking with Andrew Reinhard and Megan von Ackerman. I don't have a picture of Megan, but I recall that she studied early medieval keys, which is apropos since the discussion I had with them was really key to this work. Specifically, this is the question they asked. It speaks to how game programmers made these digital artifacts. And while it seems on the surface like only a slight variant of finding one piece of code being reused, in fact, it touches on a really tricky theoretical problem in computer science. And here's the difference. To answer the question that Andrew and Megan posed, we need to be able to answer the question, what is code? And it turns out that you can mathematically prove that's a problem you can't solve in general. However, I know what you're thinking. It's like I read your mind, right? And sometimes there's more than one way to approach a problem. We built a system I called DIS, a name chosen not for any particularly deep reason, except that's what I called the program initially and the name sort of stuck. What DIS has is an Atari-specific disassembler. A disassembler is a tool that reads bytes and converts them as well as possible into slightly higher level assembly code. And programmers writing games for the Atari 2600 would have written their code in this language. My disassembler heuristically separates the code from data at this stage. And we take a large corpus of Atari 2600 game cartridge images, 1,984 of them, and pre-process them all through this once. And as output, what that creates for each game is what I call a dump file. The dump file contains a number of things, but in particular, I want to focus on what I call bad code. What BAD stands for is binary abstracted disassembly. In assembly code, when code gets reused from one game to another, there are some things that are likely to stay the same, and there are some things likely to change. What we tried to do with this bad code is abstract away from the original assembly code, essentially throwing away the parts that will probably change from game to game, and keeping the parts of code that will remain the same across different games. In other words, what we're trying to do is strike a balance here. We don't want a lot of false negatives where we're going to miss interesting instances of code reuse, but we don't want a lot of false positives either where we'd end up looking through a whole bunch of results that are meaningful. Does this introduce some bias into the results? Totally. It's a trade-off along the path to making this a tractable problem to solve. Once we have these dump files, the workflow looks like this. We take all the dump files and automatically winnow them down into a more representative set. For example, if I have 8 prototypes of a My Littlest Pony game in the corpus of Atari 2600 games, it's not likely to give me a lot more information than simply having one of them. And in addition, it cuts down processing time quite a bit by having a smaller set of images to work with. So we narrow down the set of dump files we need to look at, and then we look for matching bad code segments across the games. Then we can take the search results and we can feed them into any of a number of analysis programs we've created. How did this play out? Well, we started with some 26,000 matches across the whole corpus, which we reduced into slightly over 3,000 unique sequences. But then when we sifted through them and analyzed them manually, we found that certain pieces of code were very popular candidates for code reuse. And I'd like to tell you the story of one of them. As a prelude, this is the result of one of our systems analysis programs. What it's doing is showing two alleged instances of code reuse side by side with the differences between the two highlighted. What you're seeing here is the code reuse I found before manually and entombed, except when I showed it to you earlier, I'd sanitized it so that it used variables W, X, Y, and Z instead of the actual memory addresses. Here it is in its raw form. This view from the analysis allows a human analyst to study and validate the results that were found automatically. And if you're wondering why I'm saying this is code reuse, when clearly there are some differences, memory locations could naturally get jostled around when code was reused, which is why we abstracted that away with the bad code. But apart from that, the code's the same. Trust me. And this result indicates different code reuse between Entombed and the well-known game Pitfall that I had no idea about previously before I ran our tools. This is a reasonably long sequence of code, and the only difference between them is, again, a slightly different memory location being used. What is this code doing exactly? The short answer is it's calculating two values needed for horizontal positioning of game objects. It's really cleverly written. Are there other ways to do this that don't use this exact code? Yes, absolutely. But where is this particular one coming from? Well, Pitfall is a game made by the company Activision. And on a hunch that code would be shared within companies, I checked out Carol Shaw's game River Raid, which would have been in development at Activision at about the same time as Pitfall, and found a perfect match for the code. Now, the source code for Carol Shaw's games was donated to the Strong National Museum of Play a few years ago, and we can actually see this in its original form that Carol Shaw wrote. And it's called Archaeogaming. Unfortunately, there's no credit given, nor would there necessarily have been if it was simply common code used within the company. This calculation code is best thought of as game infrastructure code rather than game code per se. And there's no sense reinventing the wheel for this within the same company. Now, we're also seeing this code being reused across different companies, and there's a lot more to the story here that I don't have time to talk about, unfortunately. But let's step back and view this practice of code reuse through an archaeological lens. We can certainly place code reuse within the Chan repertoire that I mentioned earlier. However, what I really like about this work is that Katie took a different theoretical direction. What occurred to her is that what we were seeing with code reuse in these digital artifacts was akin to how early humans used lithic stone technology, where we see reuse employed for both reasons of curation and expediency. And if we view computer code as not only a raw material, but a tool, we can see that programmers are really reenacting those behaviors that humans have exhibited for millennia. So to conclude, I want to return to this earlier slide, because what we have through our work are not really conclusions, but a process of ongoing discovery through these interdisciplinary methods that gives us increasing insights into humans and technology. Thank you very much.
Thanks, John.
Happy to answer all your questions.
Great. Lovely. Yeah, thank you very much. Yeah, lots to think about there. Also really, really interesting sort of history of not only of your sort of trajectory through this, but of the sort of discipline of both archaeogaming and the specific study of game code and so forth. That gives us a lot to chew on there. I sort of one sort of kickoff question, if you like, which may or may not be deeply fruitful, but just to remind everybody else, you can either ask your questions in the chat, or if you want to raise your hand, we'll invite you to unmute and ask your question in person in a moment.
I'm trying to stop the share. I'm not sure if I'm being
yes,
successful.
you have. You've stopped sharing. It's great.
Okay.
Thank you. So my question is a question which sort of occurs to me that one of the things that characterizes archaeology, especially but not only ancient archaeology, is scarcity of objects. One of the reasons we dig around in the ground and are interested in and obsessed by every single fragment we find is that finding one tiny fragment of a vase may be the only part of that vase we find, maybe the only fragment of that kind that we find. And even if we find hundreds in different places, they're all unique. And so we're constantly trying to reconstruct larger objects and larger contexts and larger practices from these tiny fragments of artifacts, of culture, etc. And I wonder, I mean, do you think that that's a difference with a lot of things in archaeogaming, and especially in the aspect of it that you've been describing, where you don't have that scarcity in the same way? Maybe with some of the earlier games, we have still some of the fragmentary nature, as in, you described how we have the code, but we don't have the source code, and we don't necessarily have personal reminiscence about it, and so forth. But in many cases, and especially with more recent games, you can still apply these technologies quite fruitfully, as you've shown, to things where there is no scarcity. Does that difference in availability of material make a meaningful difference to the way we do these disciplines?
That's an interesting question. Thank you for that. I would say that there's some subtleties to consider. So there's actually a survey done within the last year by the Video Game History Foundation, and they looked to see how many games were actually available, like in some sort of playable format. And what they discovered is that a lot of them, and for some time periods, the majority of them are not actually readily available anymore. And so while we might think of these as commodity items that are just everywhere, in actual fact, not everything is preserved in a way that we can play and experience it. And certainly, even if you have a game that is widely circulated, as you say, the original source code for that may not be available. It might be lost. It might be legally encumbered. It might be sitting in someone's garage that we don't know about. Speaking of which, I believe Paul Allen Newell actually had joined up, so I hope he's getting a laugh out of that. So yeah, the things, these digital artifacts are really ephemeral, and they may not be as prevalent as we might imagine. So, but if you think of this in terms of more, say, the scope of contemporary archaeology, where we might have a lot of modern garbage deposits, where we might have a lot of instances of these commercially produced items, we perhaps come into something which would be more familiar. So does that answer your question?
Yes, thank you. Yes.
See, there's a question in the chat.
Yep. Keith, would you like to unmute and ask the question, Keith, or should we read it out?
So and flip back here. So the Harris matrix that Katie made was representing the relationships between different versions of the code. Just reshare this here if I can.
So if you could just summarize the question, because
yeah, sure.
The recording
right, sorry, I'll read it out.
Okay, go ahead, Keith. Thanks.
Thank you, Joy. It was interesting stuff. There's lots of stuff in there, and inevitably I have to focus on this category. But I wondered if I remember rightly, was this from Entomb?
Yeah, so I'm hoping you're seeing
someone's grouped various things, because there's more than one thing in some of those boxes. Yeah. And I suppose I was just trying to ask you generally how this might work across other. This isn't particularly code, is it? But if there's actually stratigraphic relationships within other elements of code or elsewhere in the game. I mean, it just tweaked that feeling with me about the spatio. Some like the other stuff you said at the start made me wondering, these games kind of go in loops and things. So there are things which are quite different about the kind of spatio-temporal sequencing that you might encounter in a piece of dirt in the ground. And I just thought it was interesting to explore. The fact that you put this up kind of was great.
Yeah, no, absolutely. And as I mentioned, this is actually built on an idea from Andrew Reinhardt, where he was using a Harris matrix to chart the different versions of game No Man's Sky, as I recall. So basically, this came about because we ran into what was for us an unfamiliar problem, where we just had so many artifacts to deal with, and we needed to figure out some way to organize and reason about them. And so we built a catalog like you might have with finds on an archaeological site, and this Harris matrix basically allowed us to track the different versions of the code we had. So this is showing the primary versions and then the breakdowns of the individual versions that were under development. Because the record that Paul had kept was actually detailed enough that we could track through and figure out what had happened during development and what had changed from version to version. So it was really a very rich record to study. Are there other ways and other relationships that we could chart? I would suggest absolutely. I would equally suggest that we're kind of in the early days of how to apply some of these archaeological techniques to studying code. And so this is kind of a first order attempt at doing this. What I can tell you is that as a computer scientist, when Katie had suggested this, I was just like, yeah, Harris matrix, whatever. But I can tell you that when we were writing the paper, I referred to this thing all the time to figure out what was going on. Like, it was super useful in ways that I hadn't anticipated. So I guess the answer to your question is yes, I'm certain there are other ways and other relationships we could chart. But also, even just this one relationship and charting it out was unanticipatedly useful.
That's great. Thank you. And as I look at it now, I can't resist noticing that there are dates somewhere within. You've got things like January 82. I presume those are real things. Jan 82 and June 82. So there's a kind of sequence within a sequence as well in there.
Yeah, and one of the problems is figuring out how accurate the dates there are, because, well, as in archaeology too, but computers of the time didn't necessarily have real-time clocks tracking everything. And so if you find, say, a timestamp on a file or a timestamp on a printout, you need to be cautious about the context as to whether or not this is actually a legitimate date.
Oh, yeah. I think the term is residual. That's fascinating. I mean, literally, it's like they have with coins, and you get dates on coins, but it doesn't mean that's the date the coin was buried. It was the date the coin's made is different from how it could end up in the sequence. So it's great. I might well come back to use some of this elsewhere. Brilliant. Thank you.
My pleasure. I see there's another question in the chat.
Yeah, Sinead, would you like to unmute and ask that question, or should we read it out? So Sinead's question is, she's wondering how the video game companies feel about you doing in this research. Did you run into any legal or copyright issues in accessing code? And she mentions the video game preservation project at Stanford that may have had similar issues.
No, I mean, that's a good question. And yeah, certainly some of what we do will fall under copyright exemptions, fair dealing exceptions in Canada and say the UK, fair use exceptions in the US for research and teaching. What's kind of interesting is that some particularly larger game companies actually have archivists, and so they have internal archives of code. And so, for instance, for Amnesia, that was actually my starting point, was contacting the archivist there to see if we could get the source code, and through a longer story than anyone wants to sit through, the answer was no, which is actually fairly typical. So even if the code isn't lost or hidden in a garage, it may just be legally encumbered. But yes, I would also say that reverse engineering in general has a legal framework that it needs to operate in. As I'm not an archaeologist, I'm also not a lawyer. And whenever I teach my reverse engineering course, I actually have a talk from a colleague over in the law faculty that touches on these issues. But the other thing to remember is that certainly in the era I'm working in, this is some pretty old stuff. I mean, no one, while an IP may still have some value for reboots and things, the actual code and data for a game 40 years ago, in all likelihood, no one's really going to care about it. So hopefully that answers your question. Oh, from Lisa, who is the one who nudged me off in the Archaeogaming direction with her question. What advice would you give to students interested in pursuing Archaeogaming research? Certainly there are very welcoming communities in Archaeogaming. There's a long-running Discord that has lots of students and early career researchers taking part in it, which is actually one of the things that I found heartening, because when I looked at the Archaeogaming community, it seemed to me that what I was seeing is the people who would be getting their master's degrees, their PhDs, and who would be doing research in 5 and 10 years from now. So in some ways it looked like Archaeogaming, through it, I was seeing the direction that a part of the field of archaeology might be going. So it was really neat to be a part of that, particularly in the early days where it was just kind of a small group of us doing that sort of work. And certainly Archaeogaming is broad enough in terms of the topics it covers that even if someone isn't particularly technically inclined, like a lot of the work that I do, or knows someone who is to work with, there are lots of other opportunities to get involved with Archaeogaming work. I believe, if I remember correctly, the archaeogaming.com site, if I remember right, does have a bibliography of a whole bunch of different Archaeogaming publications. So you can get a sense of the scope of what people are doing. Oh, thanks, Gabby.
So you started this presentation with the disclaimer that you're not an archaeologist, but you are a computer scientist. Could you imagine somebody doing doing Archaeogaming research who would make the opposite disclaimer, say, I'm not a computer scientist or digital humanist or a coder at all. I'm purely an archaeologist and coming into it this way. Is that something that could be imagined?
I would love to see that happen. It was quite a shock to me when I started looking at research published in archaeology, looking at what they had done with relation to digital artifacts, that there just wasn't a lot of it, as in I could count it quite easily on the fingers on my hands. So yes, I think there are enormous opportunities for archaeology to move in this direction, and I would be delighted to see more of that. It may not be a case of just a lone archaeologist going and doing this. Like I say, I'm particularly keen on seeing these sort of interdisciplinary collaborations where I don't need to be an expert in everything, and neither do my collaborators. And it's through our combined efforts that we're able to do this work. So yes, more archaeologists should do this. And I actually, so a couple of years ago, I started teaching a university course, a second year university course on reverse engineering, and it is open to not only computer scientists but anyone from any discipline, as long as you have an introductory programming course of some kind. So I really think that not only people outside computer science and engineering can learn this, but also the thought processes that archaeologists, that other people in the humanities use, are actually very similar to what you would use in reverse engineering. And it's just a matter of filling in that technical gap between what they know about computers and how they go about solving these reverse engineering puzzles.
I wondered something, and again, this may be a naive question, but when you were talking about the difficulty of the problem of finding reused code, and in fact, I think you said it was proven unsolvable problem. That part of that must have been the issue of scale, because any snippet of code in any file needs to be compared to other snippets of code in other files. But it occurred to me that that must be a similar problem to genetic fingerprinting, to finding mutations, to finding possible relations where genetic snippets of genetic code wouldn't be identical, but would have to be similar enough to be matched. And presumably the code in comparing to gene maps is presumably orders of magnitude larger than most of the game code we're looking at. So is it the same sort of problem as that, or?
I mean, certainly you're right in that the comparison of all these games does take a while, but that's actually not the theoretical issue. So the problem actually derives from the fact that computers are just extremely flexible, and the language that they speak, the code, is really expressed in terms of numbers. So when we scale up this search, because we need tools to examine 2,000 odd games. So when we scale this up, we need to be able to automatically determine what is code and what is not code in order to figure out which is reused code. But the problem is that when you see a number, so I see the number, I don't know, 60 in this game image, what is that? And it turns out that the difference between 60 being data and 60 being code is whether or not the computer was at some point told to execute that particular number. And that's where the undecidability comes from. So there's some heuristics we can apply to try and figure that out. But in fact, the problem even gets even weirder because especially when you're looking at these early games. There were lots of optimizations that the programmers did to make these things work. And so it's not even just a matter of saying, oh, well, this is code and this is data, because sometimes what these programmers would do to make their games smaller is they would interlink the two. And so something that is used as data is actually code, and both are correct solutions to this problem. And in even weirder cases still, there will be sequences of code which have been very cleverly overlaid with other sequences of code. So it's a really hairy problem to sort out. So I see there's another question here. What would you conceive as the starting point of a piece of game code? And does that relate to the endpoint of reverse engineering? So what is the starting point? Usually what I do is I will start off with some sort of research question in mind. So for instance, maybe I'm interested in, I don't know, the graphics for a particular game were produced, for example. And through a variety of different techniques, ideally what I want to do is I want to hone in on the portion of the game that is responsible for that as quickly as possible. Because whenever you look at games, or for that matter, any programs, there tends to be a lot of samey code. And so if you were to start at the very beginning of a game's code and work your way through, there's going to be a lot of stuff that is not super interesting, because it's going to be exactly the same as anything else you might see. So that's one of the things that you learn as you're reverse engineering is what sort of techniques you can leverage to get to the answers you're interested in very quickly. Now, one of the advantages to digital artifacts is that, as I mentioned, you don't need to start at the beginning. You don't need to dig the top layer of dirt before you get to the lower layers of dirt. And in fact, when I was looking at this game, Amnesia, for instance, I had my research questions to begin with, but ultimately I kind of ended up bouncing around between them, because you can do that with a digital artifact. And as I learned something trying to solve this problem, I'm like, oh, okay, I can apply this over here to get more insight onto this other problem. So it's a much more dynamic and flexible approach to analyzing artifacts than certainly you might be accustomed to in archaeology. So does it relate to the endpoint? On a good day, yes. Yeah, of course, you also end up with dead ends as you're going through.
Thanks, John. So I'm not suggesting we should machine off the later stuff to get to the, but it's just the parallel there was irresistible. And it's good. It's good. It makes sense to have you've got a question. So that's, if you're seeking an answer for that question, that makes sense. Thanks.
Well, it's funny you mentioned that, because for people who reverse engineer hardware, particularly computer chips, they will actually dissolve the layers of coding on the chips in order to see the electrical traces underneath. So there's actually some truth to machining off the later layers. And I did some experiments where I was really interested in what was inside a physical game cartridge, but I mean, it's this breakable plastic that was made like 40 years ago. And I knew that if I tried to go inside, I would break this thing. So I actually found some researchers with an X-ray machine on campus and took this game cartridge and had them X-ray it so we could see what it looked like inside. So there are some actual cases in which you either machine off the later layers or dissolve the outer layers, or use an X-ray machine to use the later layers. But it's not something that's dealing with digital artifacts like I do that you would typically do.
Yeah, I think some of the these theoretical and conceptual issues I think are going to be the same, aren't they, with sort of traditional archaeology, where, for example, there's one way of thinking about it is that you're not in archaeological study, you're not necessarily reconstructing the original state of something. You're studying the evidence for that state, which may be getting you close to it, and your goal may be to get close to it, but you're this one way of looking at it is that it's not the original state that you're studying at any point. You're looking at various layers in between, which includes its historical afterlife, and that the same may be true of looking at code. You're not looking at the original state of the code, if there is any such thing. You're looking at your evidence for that, what the code does, how you get there, the data alongside the code, and things like this. So it's that sort of theoretical question, I think, is again another useful parallel between the disciplines.
Mm-hmm. Yeah, I know. There's a paper by Gabriel Mashenska where he talks about reverse engineering in archaeology, although he was thinking of it in physical terms, but he does make the case that there are these links. But again, to come back to some of the differences with digital artifacts, it is also the case thinking about these unusual situations, especially early on, but you can have code that is actually modifying itself as it runs. And so what you are seeing at one point in time may not necessarily be what you would see at a different point in time. So it's almost like reading this Harry Potter-like book where the book changes as you are reading through it. So there are some challenges in doing this sort of analysis.
Which again is fairly normal in archaeology and history to see, our understanding of the past is evolving the more we study it, and so we're never actually reaching the past, we're just reaching our understanding of it. So that's again the changing code, the moving target is a completely normal thing, probably in every humanities discipline. Actually, we're aware that that we're not at any point grasping reality, where we're approaching our view of it. Great. Cool. Well, thank you very much again, John. If anybody has any last minute questions, please do jump in, but otherwise we've reached the end of the time we had assigned for this seminar. This was, again, really exciting, really fruitful. I think the variety of different questions we've got, and also the number of people who have in the background left in the chat saying that they really enjoyed this but had to go on the hour, is evidence of how stimulating this was for all of us. But shall we all just thank John once again, virtually or otherwise, with applause? And yeah, thank you very much. It's great.
Well, thank you all. I really appreciate you coming out virtually for this.